Today's topic is about the periodic table. This session includes number 1, the periodic table, number 2, the development of the periodic table, number 3, metals and nonmetals, number 4, group 1, number 5, group 7, and number 6, group 0. This is a periodic table. We will be referring to this quite a lot in this video. To recap, on this diagram, the letter E represents the symbol of the element. The number at the top is the relative atomic mass, which is the total number of protons plus the neutrons for this element. The number on the bottom represents the atomic number, which is the number of protons or the number of electrons for this element. Each colour symbolises the type of metals and nonmetals which can be found on the top of the periodic table on this slide. We will go through some of these metals and nonmetals in more detail on this video as it's required in the syllabus. The periodic table only contains approximately 100 or so known elements, never compounds. Each element has its own chemical symbol, whereby the first letter is capital, followed by a lowercase letter. Example, so for helium, represented as a capital H and a lowercase e. The periodic table is laid out in the order of increasing atomic number so that the elements with similar properties form columns. These vertical columns are called groups, as shown in the diagram as 1, 2, 3, 4, 5, 6, 7 and 0. These can also be represented as Roman numerals. The group number is the number of electrons in the outer shell. Example, all group 1 elements, which are shown in the brackets, all have 1 electron in their outer shell, whereas group 7 elements will all have 7 electrons on the outer shell. The exception to this rule is group 0, as helium has 2 electrons in their outer shell. All elements in the same group are likely to react in a similar way. This is because elements within the same group have the same number of electrons on the outer shell. Therefore, if you know the properties of one element, you can predict the properties of other elements in that group. You can also predict trends in the reactivity, which will be explained in the next few slides. Additional information to remember: each electron shell is shown as a circle and each electron is shown as a dot or a cross. The horizontal rows going from left to right are called periods, as shown on the diagram below. The period number tells you the total number of electron shells of an element. Example, elements in period 2 have 2 electron shells in total, and elements in period 3 have 3 electron shells. All elements within the same period each have the same number of electron shells. For example, all period 3 elements have 3 electron shells. Additional information to remember is how many electrons can each shell hold. The development of the periodic table. In the early 1800s, Newlands arranged the elements by the atomic mass. Until recently, there were 2 obvious ways to categorize elements. Number 1, their physical and chemical properties, and number 2, their relative atomic mass. Once the elements were arranged in the order of the atomic mass, a period pattern was noticed in the properties of the elements. This is where the name periodic table comes from. Early periodic tables were not complete and some elements were placed in the wrong group. This was because they were placed in the order of the relative atomic mass and did not take into account of their properties. Mendeleev overcame some of the problems by taking 50 known elements and arranging them into his table of elements with various gaps. Mendeleev put the elements mainly in the order of atomic mass, but did change that order if the properties meant it should be changed. For example, iodine has a smaller relative atomic mass, but is placed after tellurium as it has similar properties to those other elements in that group. Gaps were left in the table to make sure that elements with similar properties stayed in the same group. It was only in the 20th century, after protons and electrons were discovered, that it was realized the elements were best arranged in the order of atomic number. The discovery of isotopes confirmed Mendeleev was correct to not place elements in the order of atomic mass. As isotopes of the same element have different atomic mass but have same chemical properties, it occupies the same position on the periodic table. Students should be able to describe these steps in the development of the periodic table. Metals and nonmetals. The zigzag line on the periodic table below separates the metals on the left, shaded in red, from the nonmetals on the right, shaded in yellow. Hydrogen is a nonmetal, but is often put in the middle. All metals are solids, except mercury, and nonmetals can be solid, liquid or gas. Now let's look at the properties of metals and nonmetals. Remember, atoms react to form a full outer shell by losing, gaining, or sharing electrons. The first property is chemical properties. In chemical reactions, metal atoms lose electrons to form positive ions. Example, sodium atom only has one electron on its outer shell, so it loses that one electron to form sodium ion, which is represented as Na+. The reason why metal atoms lose electrons will be explained on the next slide. Metals have less number of electrons on the outer shell, so it makes it easier to lose electrons than gain electrons. For example, sodium atom can either lose that one electron on the outer shell to form a full outer shell, or can gain 7 electrons, which really doesn't exist, but is used here to demonstrate that losing an electron is easier. Therefore, sodium atom loses an electron to form a sodium ion. This concludes metals always lose electrons to form positive ions, whereas non-metal atoms gain electrons to form negative ions. This is because nonmetals are mostly on the right-hand side, and because the group number increases to the right, this means they have more electrons on the outer shell than the left side, and it's easier to gain electrons than lose electrons. For example, looking at the fluorine atom, same as before, it can either gain 1 electron or lose 7 electrons, and it's easier to gain 1 electron to form fluoride ion. Again, losing 7 electrons for this fluorine atom doesn't really exist, it's just for your understanding. This concludes nonmetals always gain electrons to form negative ions. The second property is physical properties, which is shown on the table for metals and nonmetals. Please make sure you learn these, as an exam question could ask you to compare the physical properties of a metal and a nonmetal. Group 1. Group 1 elements are known as alkali metals. These elements are shown on the diagram. Physical properties of Group 1 are as follows. The physical state is a solid, they are all soft, they have a low density, and they have a low melting point. Remember, elements with similar properties are grouped together, and there are some trends as you go down the groups. So let's look at the trends in Group 1. Number 1. Increasing reactivity as you go down the group. This is because the atoms get bigger, the outer electrons become further away from the nucleus, the force of attraction between the positive nucleus and the outer negative electron decreases, so the outer electron is lost more easily. This makes them react readily. Number 2. They have a lower melting and boiling point as you go down the group. This is because the atomic radius increases, which makes the electrons further away from the nucleus. Therefore, there are weaker forces between the outer electron and the nucleus, so it requires less energy to overcome these forces. Finally, number 3. Higher relative atomic mass. So potassium has a higher relative atomic mass than lithium. Trends is a really good question to come up in the exam, so learn these trends. Chemical properties of alkali metals. Atoms of Group 1 elements all have 1 electron in their outer shell, which gives them similar chemical properties and makes them very reactive. Group 1 metals don't need much energy to lose their 1 outer electron, so they readily form positive 1 ions. It's so easy that they react with nonmetals to form ionic compounds. These compounds are generally white solids that dissolve in water to form a colourless solution. For example, potassium, which is an alkali metal, reacts with bromine, which is a nonmetal. This forms an ionic compound called potassium bromide. Students should be able to write word and balanced chemical equation for the first 3 alkali metals with water, chlorine and oxygen, and also describe these reactions. This is going to be covered in the next few slides. Reaction with water. All Group 1 metals reacting with water form metal hydroxide and hydrogen gas. Alkali metals dissolve in water and form alkaline solutions. This is a solution that contains hydroxide ions. The red writing in the text box is the generic equation for this reaction. So a metal plus water gives you metal hydroxide and hydrogen. An example of sodium reacting with water is shown. Additional information for your own knowledge is to understand what these state symbols stand for. So S for solid, L for liquid, G for gas, AQ is for aqueous, and this means compound is dissolved in water. So as you go down Group 1, These reactions will fizz vigorously as the reactivity increases. From potassium and below, it's hot enough to ignite hydrogen. And finally, as you go down the group, the amount of energy given off by the hydrogen gas increases. The next one is reaction with chlorine. All group 1 metals, when heated with chlorine gas, form white precipitates called metal chlorides. The general equation is metal plus chlorine gives you metal chloride. An example of sodium is shown. As you go down the group, the reaction with chlorine becomes very reactive. Reaction with oxygen. All group 1 metals react with oxygen from the air to form metal oxide, which is a white oxide. The general equation is metal plus oxygen gives you metal oxide. An example of sodium is shown. Different types of oxide will form depending on the group 1 metal. Lithium reacts to form lithium oxide. Sodium reacts to form a mixture of sodium oxide and sodium peroxide. Alkali metals must be stored under oil to prevent them from reacting with oxygen and water. This table summarizes the reaction of the first 3 alkali metals discussed on the previous slides. Group 7. The elements in Group 7 are known as halogens. These elements are shown in the diagram. Group 7 elements are on the right-hand side and they are all nonmetals. So let's look at the physical properties. Halogens exist as simple molecules. This means each molecule is made up of a pair of halogen atoms joined by a single covalent bond. For example, F2, Cl2, Br2 and I2. Halogens also have a higher melting and boiling point. The physical state, which means how they actually exist, and the colour of the halogens are shown on the table below. The trends for the halogen as you go down group 7 includes: number 1. They become less reactive as you go down. This is because the atoms become larger, the outer shell becomes further away from the nucleus, the force of attraction between the nucleus and the outer shell decreases, which makes an outer electron less easy to be gained. Therefore, halogens become less reactive. Here in Group 7, we talk about an electron being gained, whereas in Group 1, we spoke about an electron being lost. This is because Group 1 are metals and Group 7 are non-metals. The next one is they have a higher melting and boiling points as you go down the group. This is because as atoms become larger, there is an increase in the number of electrons in each atom, leading to greater intermolecular forces between the atoms. Therefore, more energy is required to overcome these forces. Number 3, the relative atomic mass increases as you go down the group. And finally 4, the state changes from gas at the top of the group to solid at the bottom. Chemical properties. All the halogens have similar reactions because they all have 7 electrons in their outer shell and they are less reactive. Note: students should be able to describe, write word and balanced equations for when chlorine, bromine and iodine reacts with metals and nonmetals. Reactions with nonmetals. Halogen atoms can share electrons via covalent bonding with other nonmetals to achieve a full outer shell. For example, when chlorine, which is a halogen, reacts with hydrogen, which is a nonmetal, hydrogen chloride is formed. This is a gas and has a chemical formula HCl. Hydrogen chloride dissolves in water to form hydrochloric acid, which has the same chemical formula as HCl but is differentiated by the state symbol. Compounds that form when halogens react with nonmetals all have simple molecular structure. Reaction with metals. Halogen atoms form -1 ions called halides. For example, fluorine atom becomes a fluoride ion. When these halides bond with metals, they form compounds called ionic structures. An example is shown below. Ionic structures will be covered in more detail in the bonding video. Displacement reaction. A displacement reaction can occur between a more reactive halogen and the salt of the less reactive one. A more reactive halogen can displace a less reactive halogen from an aqueous solution of its salt. So, looking at this example below, potassium iodide is a salt, and for this displacement reaction to take place, it must be in the form of an aqueous solution. To do this, water is added. Chlorine is more reactive than iodine, so when chlorine is reacting with a solution of potassium iodide, chlorine displaces iodine and forms potassium chloride and iodine, which is shown as a balanced chemical equation on this slide. It doesn't matter what metal is used in the salt, so it could be potassium iodide or sodium iodide, and you will still get a displacement reaction because it's about the more reactive halide displacing the less reactive one. What happens during the displacement reaction? Before starting the experiment, the colour of the solution in the test tube tells you which halogen is present. Bear in mind, the physical state of halogen can be a solid, liquid or gas, therefore water is added to make it into an aqueous solution. So chlorine solution is pale green, often colourless, bromine solution is yellow, and iodine solution is brown. Once the salt is added and a displacement reaction takes place, then the solution colour in the test tube will change. So, chlorine solution in the test tube will be a pale green colour, and once the salt, which is potassium iodide, is added, a displacement reaction will take place, as chlorine is more reactive than iodine. So the colour of the solution would change to brown as iodine has been displaced. The least reactive halogen cannot displace the most reactive halogen. For example, if potassium chloride was added into iodine, which is a brown solution, the iodine cannot displace chlorine. Therefore, no reaction takes place and the colour of the solution remains brown. This table summarises the reaction of each halogen solution. Group 0. The elements in Group 0 are known as noble gases. These elements are shown in the diagram. Group 0 is on the far right-hand side of the periodic table. They exist as monatomic gases. So let's look at the physical properties. All elements in Group 0 have low boiling points in comparison to elements of other groups. They are inert, which means they are extremely unreactive. They are non-flammable, and they are colourless and odourless gases. Additional info. Although noble gases are colourless, they give out a particular colour of light if you pass an electric current through them. For example, helium can be seen as pale yellow to orange colour, neon can be seen as red glow, and argon can be seen as blue. The trends for the noble gases as you go down Group 0 includes: number 1, increasing boiling points. This is because atoms are larger as there is an increase in the number of electrons in each atom, leading to greater intermolecular forces between the atoms, therefore more energy is needed to overcome these forces. And the second one is, as you go down the group, there's an increase in the relative atomic mass. Next is the chemical properties. All the noble gases are extremely unreactive and do not easily form molecules. This is because they all have a full outer shell, which makes them energetically stable. This means they do not need to gain or lose electrons to become more stable. Hence, they are unreactive. Helium has 2 electrons on its outer shell, and the other noble gases have 8 electrons. By the end of this session, students should be able to describe the position of the element in the periodic table related to the arrangement of the electrons, describe the steps in the development of the periodic table, explain the difference between metals and non-metals based on the physical and chemical properties, explain the physical and chemical properties of Group 1, 7 and 0, and finally predict properties from given trends down the Group 1, 7 and 0. Thank you.